Hey guys, how you doing today? We're gonna talk about derivative notation. So we're gonna start off easy. We're gonna begin with the notation that probably all of you know, f prime of x. We know f prime of x is generally used when you're going to set up the definition. So you say the derivative f prime, or f with the apostrophe, is the limit as h approaches 0 for a function f of x plus h. Remember, you're trying to bring up to move the point h units minus f of x divided the change in x, which is just simply h. Okay, so this is you're normally gonna see this notation when you're defining a derivative through the definition. Okay, now let's continue with some more notations. Now another one that you may have seen is this one, dy over dx. Now this is called Leibniz notation. Now the thing about Leibniz notation is that, first of all, don't be scared by the d's or by the letters. I'm going to show you what they mean. So basically, dy over dx is just saying the difference in y over the difference in x. Okay, that's what d means. Okay, you could also say that d is a differential. We're gonna see in following videos what differentials are, but it's something pretty easy. Okay, you're gonna see it particularly with integrals. You're going to understand what a differential is, but for now, don't worry about it. Just know that this is saying the difference, and a difference as a limit. So you would have that basically dy is saying dy over dx is just saying a limit. You could say limit in y, or a difference that can be seen as a limit in y over a limit in x. Now, why am I saying that a limit on top and bottom? If you see this form, basically what you're doing when you say the limit as h approaches 0, this is almost a division of 0 by 0. Because if h is a very small number and you have f of x plus h, that is almost the same as f of x. And also here, well, you've got 0 too. So if you have two things that are very similar, well, you're gonna get a difference of them that is very close to 0. That is why it is approximately dividing 0 by 0. So that is why in this case we say the limit top and bottom. Okay, that is what d means, just difference in something. Now we've also got another notation that can be, well, you could say maybe derived, maybe not derived, but that has a very close or tight relationship with Leibniz notation, and is the following one: delta y over delta x. Now there is some discussion about that. This is implying, or this is saying, average change. Remember that if you have, for example, an example of delta y over delta x is the equation that all of you know for the slope. This is a very common equation that all of you know, and this is basically just saying, not in infinitely small scales, what is the change of y divided the change in x. Okay, this is delta. Remember, delta means change. Okay, the change in whatever variable you've got over there. Now this is virtually the same thing as if you said dy over dx. Okay, because here you've got a difference, you've also got a difference here, and you've also got a difference up here. Okay, and well, of course, in the bottom too. So basically all these notations, they are almost the same thing, and I say almost because I'm going to show you something now with Leibniz's notation. But what I'm just trying to show you is that all these things, they represent the same idea. Okay, and you must be familiar with them when you're doing all types of calculus. Okay, so now let me show you something about Leibniz. Now the thing about Leibniz notation is that it's pretty interesting to use this form. So you have the difference of an output. Now I'm going to write it like this so you see what I'm doing, or what I actually mean. You have the difference of an output divided by the difference of an input. Okay, in this case, output and input refer to the parts of a function. Okay, you've got an input that in single variable calculus is, well, most of the times x, or just one variable, and you've also got one output. Okay, and so with this, if we say, for example, that y is equal to the output, so we say f of x, and now the input, in this case, well, clearly it's just gonna be x, we would have that this is just simply dy over dx. But now, what if we had a function that has maybe a couple more variables or terms, okay, without necessarily getting into partial derivatives, which is what we use in multivariable calculus. But don't worry about that for now. Just let me give you this example. What if we said that the volume for a cylinder, which we know is just simply the area of a circle times its height, is this equation right here. What is the derivative of the volume with respect to the height as an input? Okay? Now, in this case, it's very useful to use Leibniz's notation, because when you have, in this case, you can assign different inputs and one output, okay? So you say, for example, in this case, the input we're going to be playing with is okay, we have the output dV, or just V, volume, with respect to the height as an input, okay? So we're saying the derivative of the volume with respect to the height of the cylinder, okay? And now it is very useful because we could also say that we've got the following. This is not the same thing, remember. In this case, the derivative would change. You could also say you have the derivative of the volume with respect to the radius, okay? And this is where Leibniz's notation comes into play. Now, there is something that you may have seen before, and is the following thing. A lot of times you see this, d over dx, and an expression in here, okay, which we're just going to say is x squared. Now, what does this part mean over here? D nothing, okay, d nothing over dx, or d input, is just simply the derivative operator, okay? In calculus, we've got operators, or things that create some sort of change or modification to a expression or a function. In this case, when we say d something over dx, or in this case you're not multiplying, don't confuse like multiplying these two, this fraction with this expression, no. In this case, what you're saying is that you want to use the derivative operator in this function, okay? So what does it mean to use the derivative operator? Well, that's just simply taking or finding the derivative of the function that you've got. So for example, if we say take the derivative, or find the derivative of 10x squared. This is an operator that is telling us to do something on this function. Now, what is the derivative of this? If we use the power rule, we would know that this is 20x. Now, there is a difference with this and this. That is a bit small, but you guys see it. I know, actually, yeah. Let me write it again. So there is a difference with this and with this thing in the bottom. This is an operator, and this is technically a variable, or maybe a quantity or a value that represents something. This is saying what is the derivative of the function y, and this is saying find the derivative of the function y, right? So in this case, if we say, for example, that y is equal to 10x squared, then the 10x squared over dx is going to be the derivative of this function. And dy over dx is going to be 20x. Okay? Now, that is the main difference between these two guys over here, which are generally used, without making any differences between them. And numerically, you might not get any different answers, but I think this is probably the right way to see it. This is an operator, and this is a variable, or the representation that you're using to represent how much or what is the value for this operator in a specific, or being applied to a specific function, okay? So remember, these two guys, they're not the same thing. This is an operator, and this is technically the variable in which you are storing or representing what you got from this operator, okay? So I hope you guys enjoyed this video, learned something today about derivative notation, and see you in the following one.